In the last video I gave you a recap of basis transformation between Cartesian coordinates from linear algebra. If you skip that, here is the introduction again. If you watched the last movie, you can skip the first 2 slides of this movie and then dive into the new content. We have 2 pictures of strawberry cakes here. One is baked on a tray and the other in a round form. To order a piece of the left cake, we specify the width and height, that is the horizontal and vertical edge lengths of the piece. For round cakes, we choose the diameter of the cake and then give the angle between the cuts. Naturally, we use different coordinate systems here. Cartesian, that is x and y coordinates for the cake on the tray, and polar coordinates, that is the radius and angle for the round cake. We're using the symmetries of the cakes, and the description of the pieces is much more natural and easier in one coordinate system than the other. Of course, one can also describe both pieces and both coordinates. The change between them is a function which is called coordinate transformation. Coordinates describe a point of a space with respect to a basis. Without knowing the basis, coordinates are meaningless. The summary from the last video: to change the coordinates v1, v2 of a vector v that is given into the b basis to coordinates in the a basis, multiply the coordinate vector of the b basis with the transformation matrix T. So the vector in the coordinates with respect to the a basis is obtained from T times the coordinate vector in the b basis, and the transformation matrix T you get by writing the coordinates of the basis vectors of the b basis given in the a basis as its columns. So the first column is the image of 1, 0, the second the image of 0, 1. If we were in 3 dimensions, the first column would be the image of 1, 0, 0, the second column would be the image of 0, 1, 0, and the third would be the image of the third basis vector 0, 0, 1. And the change of the area that is caused by this transformation is given by the determinant of this matrix. Polar coordinates. This is pretty much the same as complex numbers, if you know these. So each point in R2 is given as the distance from the origin to that point. That is the length of the vector, which is called radius usually, because think of the cake, and the angle from the x-axis to this vector, where we count counterclockwise. Now, if we know the length of the vector and the angle, then the point in space is completely determined. This description is called polar coordinates. For v, we could give rv and phi v the length of the vector v and its angle to the x-axis as the 2 numbers in a vector, and this is the coordinate vector of v with respect to the polar coordinates. If you think in complex numbers, the x component would be the real component and the y coordinate is the imaginary component. And you also know that you can write complex numbers as the length of the vector and the angle between the x-axis and the vector, and that's exactly what polar coordinates are doing. How do I go from polar coordinates to my standard Cartesian coordinates? This is a coordinate transform, and how do I get that? Well, we know that the x-coordinate of v is rv, the length of v, times cosine of the angle between the x-axis and v, and the y-coordinate is the vector projected on the y-axis, that is the length of the vector, so rv, times the sine of the angle. Of course, we can also go in the other direction, that is getting the polar coordinates r5 from the Cartesian coordinates xy. Then r is the length of our vector, this is x squared plus y squared, square root of that, and phi is the inverse of the tangent of the ratio y divided by x. So far the situation doesn't look so different from the linear algebra case. We have a xy basis and somehow a r phi basis, and we can describe every point in R2 in one or the other, and we know how to go from one description to the other description. But something is very different. Actually, a few things are very different. First, the transformation is not linear. So here what I mean is, take the vector u, that is the sum of 2 times the vector v plus the vector w. This is written in red. And the coordinates of this in Cartesian coordinates are the radius times cosine of phi u, and y coordinate the radius of u times the sine from the x-axis to the vector u. And whereas the radius is still just the sum of radii of 2v and w, this is not the case for the angles. The angle to u is not the sum of the angle to v and the angle of w. That is, this is not a linear function. The second difference, but we will see that in a few slides, is that we're not going from R2 to R2 actually. So let's first look where the points and their images are with respect to the coordinate transform from the polar coordinates to the Cartesian coordinates. Let's look at a few example points. So on the right in Cartesian coordinates, we have the point with coordinates 0, 2. That's indicated with a red X. And how do we get its polar coordinates? Well, the length of the vector is 2, and the angle from the x-axis to this vector is p half, and this is what you see on the left. There we have the two axes r and phi, r for the radius and phi for the angle, and the pre-image of the coordinate transformation from the polar coordinates to the Cartesian coordinates of the red point cross is 2 pi half in polar coordinates. Same for the others, for example for the square with Cartesian coordinates -1, 0. This means length is -1. No, wait, length is positive, so length is 1. And the angle is pi. And that's what we have in polar coordinates. Polar coordinates, 1 pi of the square. For the round circle, this has almost 2 pi as angle and is about 3 in length, so we have polar coordinates 3, 2 pi. There's a 2 cut off at the left of the picture. So what is the domain and the image of our coordinate transformation from polar coordinates to Cartesian coordinates? Well, the image is all of R2. We get all points in our R2, but in polar coordinates we actually are restricted to positive R direction. We don't have negative radius, and angles between 0 and 2 pi, with 0 included and 2 pi not included. Because if we have a vector with angle between the vector and the x-axis, let's say theta, because here I wrote theta for the angle, then if we add 2 pi to the angle, we end up at exactly the same point. This means our polar coordinates would not be unique. We restrict to one of the periods. That I wrote here theta instead of phi. Theta and phi are usually the Greek letters that are used for angles. Doesn't matter which one you choose as long as you stay consistent. So here we have the second big difference to basis transformation between Cartesian coordinates. Namely, the polar coordinate is a bijection between this ribbon that is 0 to infinity cross 0 to 2 pi and R2. That's funny. Think about that. The whole R2 is mapped onto this ribbon and the other way around. 1-to-1 bijection. Okay, great. Now we can start using that. For example, it was really complicated and annoying to compute the area of a disk in Cartesian coordinates, if you remember. So now instead let's go to the pre-image in polar coordinates, and that should be really easy. Namely, the disk drawn here on the right has pre-image this rectangle on the left, which is from 0 to r, the radius of this. Oh, I should have chosen a different r, but okay, to the radius of this disk, and all angles are passed, so from 0 to 2 pi. That means this has area r times 2 pi, and wait, that is not the same what we expect. We know already that the area of a disk is pi r square, so why do we have 2 pi r in the polar coordinates? We want to get the same thing, right? So we have to work a little bit more, or rather we have to understand one more thing. The thing to understand is the area changes. Well, that we had already in the linear coordinate transformations, but here the situation is a bit worse because it's not linear. The area changes, and it changes differently in every point. Okay, let's look at that. If we have this little black shaded segment on the right, its preimage is this nice rectangle drawn on the left, and the image of the coordinate transform of the nice red rectangle on the left is the red segment on the right. Make sure you agree with me on that. So now it's pretty clear, in the polar coordinates these two rectangles have the same area, but their images do not have the same areas. The black segment on the right in Cartesian coordinates has much smaller area than the image of the red rectangle. That means if we want to compute an area as this of the disk in polar coordinates and get the same area as we expect in our Cartesian coordinates, we have to make up for the change of the area that our transform is causing, just as before, but we cannot just multiply with the same constant everywhere as in the linear function case. We now have to multiply with a function that for each point makes up for the change of the area in that point. And that's what we're going to do. And how to do this? This is the main reason why I do this after we have done differentiation in multiple variables, and why I recalled the stuff from linear algebra and how to compute the area spanned by vectors. On the left in grey is a coordinate grid of polar coordinates shown. The grey distorted grid on the right is its image in Cartesian coordinates. This helps us to visualize the function, because the coordinate transformation is a function from a two-dimensional space to a two-dimensional space, meaning we cannot use a 3D plot to show the image as for a function with only one output. Instead, imagine the domain as a flexible cloth, and the function is distorting it until it looks as on the right. To see how the area changes under this transformation, let's see how one moves on the grid on the right if one travels along the grid on the left. If we start in the red point P and move in R direction, the image travels on the radial line outwards. Same if we start in the orange point Q. Also, we do not accelerate or slow down in speed. If we move our point along the phi axis, its image travels along the circle. And if we move at the left with constant speed, still starting in the orange point Q, the image moves much faster than if we start in the red point. Same thing, the image of the square with both edges length 1 in the orange point is much more stretched than the image of the square at the red point. To get this quantitatively, we need to know how fast we are moving in R or respectively phi direction, and also where we end up, the direction of travel in the image. This shouts for partial derivatives. Let's look at the image of the yellow point Q. If we move Q along the R axis, its image TQ in Cartesian coordinates moves on the radial path, so a bit increasing in the x coordinate and a bit increasing in the y coordinate. How much it moves into x direction is given by the partial derivative of the first coordinate function, x equal r cosine phi, differentiated for r. The value of this derivative is the length of the khaki colored vector. And in y direction, we change as much as, well, the function that gives the y coordinate changes if we move in r direction. That is, by definition, the partial derivative of the second coordinate function. Here, y equal r sine phi, differentiated for r. The value of this derivative is a dark green colored vector. Same way of arguing if we move q along the phi axis. Then the image moves on the circle of radius 3 in the Cartesian coordinate system. And in the point directly, the direction is given by the tangent to the circle, and we move a bit in x and a bit in y direction. Namely, in x direction, the change is given by the partial derivative of the first coordinate function, x equal r cosine phi, differentiated for phi. This is minus the length of the purple bar. And the change in the y direction is given by the partial derivative of the second coordinate function, y equal r sine phi, differentiated for phi, yellow. Remember that derivatives give the slopes of tangents in a point. To get a slope in one dimension, I always said, how much do I go up or down if I move one step to the right? Now for the area, if I can go at most one step to the right and up to one step to the front, that covers an area of 1 square units. And this area is mapped to the area that one can cover if moving in the image as far as the vectors that we just constructed. The vectors that tell us how far we move and in which direction, starting from tq, if q is moved in polar coordinates with constant speed 1, are the vectors whose entries are the partial derivatives by r respectively by phi. That's what we just concluded. Now we only need to know the area that is spanned by these vectors. And we know from linear algebra that this is given by the determinant of the matrix whose columns are the vectors that span the area. Writing down the entries of the first and second vector, you see that the matrix is the Jacobian of the transformation. That is not surprising, as the Jacobian is the first derivative of the function. In higher dimensions, that is if, for example, we change coordinates from a three-dimensional space, such as spherical coordinates, to another three-dimensional space as Cartesian coordinates x, y, z, everything is analog. The volume element changes. We have a cubical grid in 3D that is mapped to a distorted grid, and the change of volume is given by the change along the three coordinate functions, that is, by the determinant of the Jacobian that now is a 3 times 3 matrix. So that means the change of the area in the point in polar coordinates is given by the determinant of the Jacobian of the transformation in this point. Intuitively, if I change in r direction, how much do I change in r direction? How much do I change in phi direction? That gives exactly the stretch or shrinking, the distortion of the area that we have. And this we get by looking at the first derivative. We have derived and once gone through the whole procedure of how to get transforms between any kind of coordinate for a space and how to get the change of the area, or if we were in 3D, of the volume element that we also need for integration. Computationally, how to do this? Recap, write down the transformation of the coordinates, that is a function, approximate that by a linear function, that is the Jacobian matrix, and the change of the area element or the volume element, or in 4D, well, four-dimensional volume element, and so on, is obtained by computing the determinant of the Jacobian. And then you know how to transform the volume element from one to the other. You just multiply with the determinant of the Jacobian, and that makes up for any change of volume or area in your transformation, and you can happily switch from one to the other. When is that of interest? That is either of interest when your boundaries are much easier to get in one than in the other coordinate system, and or if your function has a symmetry that is compatible with one coordinate system or the other. So if we were integrating over a function on the disk that is given in x and y coordinates, we have to first replace every x and y with a description of the function in r and phi coordinates, so that can also be a bit of a pain. So in practice it depends on what makes life easier, and then you choose that. Now let's compute the Jacobian of the transformation from polar coordinates to Cartesian coordinates and its determinant. First, Jacobian of the coordinate transformation is first line the gradient of the first coordinate function, second line the gradient of the second coordinate function. So r times cosine of theta differentiated for r is cosine theta, that's the first entrance of the matrix. Then differentiated for theta is derivative of cosine of theta is minus sine of theta, and r is just a constant if we differentiate for theta. So minus r sine theta is the second entry. And for the second row, we differentiate the second coordinate function, so y. R times sine of theta differentiated for r is sine theta, that's the third entry of the matrix. And left is r times sine theta differentiated for theta, this is r times cosine of theta. Now the determinant of this is r cosine square theta minus r times sine square of theta. If you don't remember how to compute a determinant, go back to linear algebra. For the 2 times 2 matrices, it's the first entry times the fourth entry minus the second entry times the third entry. And that is r times cosine square theta plus sine square theta. And since cosine square plus sine square is 1, thanks to Pythagoras, the determinant is r. Yippee-doo. That means we now know how the area changes in each point, namely it's r times the area. And that is what you would see in the picture already. The segments on the right, if we make them very small, are almost rectangles with one side delta r and the other side delta phi times r. This is a segment that is more and more stretched when we go farther out away from the origin. And this times r is the stretching factor that we just computed as the determinant of our Jacobian. Now we have everything. We can make up for the change of area in the transformation and happily work in polar coordinates. So to compute the area of the disk in Cartesian coordinates, we have the y and the x integral. We integrate over 1 because there is no function, we just want the area dA, where the little a is the area element in xy coordinates, and that is exactly the one that's not the same in the polar coordinates, so we replace it with r times dA to have the surface element in polar coordinates times the factor that this one stretches to get the one in Cartesian coordinates, and integrate now somehow in phi and r, and that gives us that the area is r times dr d phi. From where to where should we integrate? Well, the radius goes from 0 to r and the angle from 0 to 2 pi. Now we have something really easy. We have the integral first integrated for the radius. This is a half r square, where r is the radius that we have there, minus a half 0 square. Okay, falls away. And now integrate this one from 0 to 2 pi is a half r squared 2 pi, and that is pi r square. Yes! Okay, now we can do exactly the same game with other coordinates. For example, with spherical coordinates. That's like polar coordinates but in 3D. So again, we have a radius that is larger or equal than 0. That is the distance from the point to the origin. And now we have two angles, theta and phi, where theta in this picture, and I think this is the standard convention, is from the z-axis down, and phi is as beforehand in the xy plane counterclockwise. So theta here is from 0 to pi, and phi goes from minus pi to pi, and then we cover the whole space. The coordinate transformation is r times cosine phi sine phi. Y is given as r times sine phi times sine theta, and that is only dependent on theta. That is r times cosine of theta. You can take a moment and double check that. This is all playing around with cosine and sine as in one of our first weeks. Now the Jacobian, this is first row, the gradient of the function that gives x. Second line, y differentiated by first r, then theta, then phi. And the third row is z equal r times cosine theta, first differentiated for r, then differentiated for theta, and differentiated by phi. It doesn't depend on phi, so that's 0. Now the determinant of this Jacobian is r squared times sine theta. So this is the change of volume that we have in each point and have to multiply under the integral if we compute in spherical coordinates to get the same what we would get if we compute in Cartesian coordinates. There's an example on the next slide. You can find the example also in the book. It's example 4 of section 14.6. And we should compute in spherical coordinates. What do we have? A solid half ball H, it's drawn below, of radius a, with a density rho equal k times 2 times its radius minus r, where k is a constant and r is the distance to the origin. Find the mass of H. Okay, so the mass is the integral over the half sphere, and we write as a function the density in there times the volume element. Now a half sphere screams for spherical coordinates. So I want to work in dr, d phi, d theta, and to get the volume right, we have to multiply whatever is written under the integral with r squared times sine phi, because this is exactly the factor we had at the last slide that makes up for the error we do in the volume if we compute in spherical coordinates. That's the transform. Or actually, I shouldn't call it arrow. This is how the transformation of coordinates stretches the volume elements when it maps them to the volume elements in Cartesian coordinates. And the k times 2a minus r is just the function that is given here as the density. Okay, word close on the face, and now it's nothing else than usual computation of integrals, and the only interesting thing is getting the boundaries right, and now the boundaries in spherical coordinates are much easier to get than in Cartesian coordinates. This is why we did this. Also in this case we don't have any conflict of interest with the function given, nicer in Cartesian coordinates because it depends on r, so also screams for spherical coordinates. Okay, what are the boundaries? The boundaries in r direction, we go from 0 to a, not starting at minus a because there we go with the different angles. The angle for phi is from 0 to pi half because we only have the upper half of the ball, and for theta we go from 0 to 2 pi once around the whole circle. If I changed phi and theta, you have to make sure that the order is right. So the second integration variable is the one where I want to go from the angle that I count from the z-axis. And the rest is standard integration, one integral after the other. I'm not reading this out, just pause and read it yourself, or even better, open the book at example 4, close the video for a moment and do the exercise yourself again and compare with the slide. Let's do a second example in spherical coordinates because I think the book has not much more given that you could read. So compute the integral over the domain S of the function x squared plus y squared plus z squared, square root of that, dx dy dz. So that is given in Cartesian coordinates apparently, where the region S is the shell of a sphere between the radius r1 and r2. R2 should be the bigger radius, R1 the smaller radius, both of them larger than 0. So first we have to replace the function by something in polar coordinates. And here this is nice enough because you see that this function is nothing else than the length of the point with coordinates x, y and z. So this is r. This is where the first r factor under the integral comes from. Then we have the r squared sine phi again, which is the transform of our transformation that makes up for the stretch of volumes. And we have dr, d phi, d theta, because now we're in spherical coordinates. What is left as real work is we should get a shell of the sphere between these radii correctly, but that in spherical coordinates is really easy. The radius goes from r1 to r2, and to get the whole sphere we go from minus pi to pi and from 0 to pi. We cover all the angles. And the rest is again computation of one integral, another integral, a third integral, and I'm not going to read it out, but you can hopefully practice it by yourself and then compare with what's written on this slide. Here's the overview of the different coordinate systems, the name of the coordinates, the transformation from those to the standard Cartesian coordinates, the determinant of the Jacobian matrix, this is a factor that you should write under the integral, and the volume element. So for example, for spherical coordinate systems, the volume element in Cartesian coordinates dv is r squared times sine theta, the determinant of the Jacobian matrix, times the volume element in spherical coordinates dr, d phi, d theta. The area changes just the same way. There is the r squared sine theta, but then we have d phi, d theta because we do not change in r direction if we only look at an area. This is like a restriction of the spherical coordinates to the shells of the balls. The only thing we have not done here is cylindrical coordinates. This is polar coordinates in the xy plane and Cartesian z coordinate in the z direction. If you want to check that you have really understood the whole concepts, here you have the determinant of the Jacobian matrix and the transformation to Cartesian coordinates to compare to. Try to derive it yourself. This is like a bonus exercise for those who really want to check that you have understood the content very well. The way of doing coordinate transformations is always the same. If you know your Jacobian matrix, write it under your integral, and that's all you need to do. Besides, making sure that if you work in polar or spherical or cylindrical coordinates, you do not have x, y, and z in your function, but have expressed them in your new coordinates. And the other way around, if you work in Cartesian coordinates, there shouldn't be a r, a phi, etc.